Hello guys, welcome back to John's Workshop, and in this video we're going to do another one in the Workshop Tips series. So this is number 6 in that series, and this is really closely linked with Workshop Tips number 4, which was a very successful video, and if you've not seen that, please go and watch it if you're watching this one, because these two are intrinsically linked. And in number 4 I talked about the process of using balance cuts to hit your sizes, and you know, even if you've watched that and you've not yet put it into practice, go and watch it again and go and try it, because believe me, once you've done it and mastered it, you will never go back to the old-fashioned ways of creeping up on a critical dimension, taking tiny little skim passes to try and hit your numbers, and then probably overshooting, going undersize, and then having to remake something, or getting within a thou of where you need to be, and then using emery cloth to try and get your finished dimension. It's not an effective or an efficient way of hitting finished sizes, and it's not predictable. It's completely unpredictable. So these two are linked, and in that video I spoke about lathe push-off, and I had quite a few comments to say, what is lathe push-off, and could I go into a bit more detail? So that's effectively what this video is going to be about. So we're going to do a bit of blackboard stuff, or whiteboard stuff. You can tell how old I am there, can't you? And then we're going to go over to the lathe, and I'm going to show you where I can what lathe push-off actually looks like on the lathe. So without any more babbling, I'm going to wipe the board clean. I'm going to get myself a bit of space and a pen that works, and I'll bring you back in at the board and we'll start to discuss what lathe push-off actually is. Okay, so we're going to try a bit of a different camera angle that I've not used before. So, and apologies, we're going to go back to school, college or university maybe. So we're just going to look at Newton's third law, which states for every action there is an equal and opposite reaction. A very, very simple law, and it's universal. And in this occurrence, while we're talking lathe push-off, I'm going to translate the word action into a force. That's all you need to know. So for every force there is an equal and opposite reactive force. So that's the law, very simple. And we're going to decamp from the board and move over to the lathe just to do a bit of familiarization with what a center lathe actually has in terms of interfaces. Okay, we're over at the lathe and we're staring at the business end, the bit that does all of the work. So what am I meaning when I'm saying interfaces? Well, let's just strip it down and have a look. So initially my tool is clamped into my tool holder. That's one interface. My tool holder is then sat onto the tool post, which is a second interface. Now those two interfaces are quite solid and rigid, and the design of both of those interfaces should be that when they're mated they're not meant to move. So they're pretty solid interfaces. However, in the case of the tool holder to the tool post, if there is errors, or there is wear, or there is damage on your tool post faces or your tool holder itself, or you've got swarf trapped behind, and I don't know if you ever see me on the lathe, you'll always see me clean the V's before I ever do a tool change, to make sure, for two reasons: one, that I'm not clamping up on swarf and compromising my setup, and second, that I'm protecting the life of my tool holders and my tool post. Very important hobby horse of mine. See so many people on YouTube not doing that and crushing bits of swarf between tool post and tool holder, and it irks me, because it's bad practice. So I've gone down a rabbit hole, I apologise. So two interfaces, pretty solid. Okay, so let's move further back. We'll take the tool holder off just for visibility. So next, my tool post is fixed to the top of my compound slide. Now that is meant to move, but it has got a clamp on it, so that has the ability to swivel and has the ability to be clamped up. Now if that face on the bottom of the tool post or the top of the compound slide isn't exactly flat, even though you've got that clamped, there will be an element of appreciable movement in that tool post under force. We'll then look at the rest of the interfaces that we've got. So how many have we got there? 1, 2, so that's 3. So we're going to keep counting. So the fourth interface is the compound slide itself. And this is where things start to get complicated, because these interfaces are absolutely meant to move. They're designed to move, and they're designed to move while the machine's actually cutting metal. Therefore, there has to be an element of play and clearance between the two mating surfaces. Now that should be at an absolute minimum, and there's a gib strip to control that on most slideways, but regardless of that, there is still free movement between those two surfaces, which means there is probably an element of play in that interface, which again is minimised by the gib strip. We've then got the compound slide bolted onto the cross slide. Now that is a fixed interface during cutting. It doesn't move while you're actually cutting, but again, same as the tool post, if the underneath surface of the compound slide or the top surface of the cross slide isn't exactly flat, again you've got the same issue where you could have movement under force, under load. We'll then look at the cross slide to the saddle. Exactly the same deal. It's a moving interface that's meant to move during the cutting of material. So again, there will be an element of free play in there, again controlled by a gib strip to try and minimise that. So I've lost count of the interfaces, but I'm sure you're keeping up. We'll now move to the next one. So we've now got the carriage on the bed. So that's really the last interface in the stack up. And again, it's a moving interface, it's meant to move during machining, so again, therefore, there could be an element of play in that interface, especially in an older lathe that's had a lot of wear close to the chuck, where the slideways are worn and things don't necessarily fit, and the play could be this way, it could be a crabbing type of play, it could be any play, but largely will be induced by the forces that you put on the entire system. So that's just a bit of a system breakdown. We're going to move back to the whiteboard now and talk about those equal and opposite forces. Okay, we're back in the classroom, so let's see how well I can draw. So let's go back to our lathe. I can't draw very well, that's my workpiece, it's slightly out of round, but let's not worry about that. So that's an end on view, as though we're looking at the chuck from the end. That's my workpiece. So if we now draw our cutting tool, so we'll draw a diameter that we're turning that's equally out of round, and we're now going to draw our cutting tool that's cutting that diameter in place. So there's our cutting tool, turning this diameter, moving into the whiteboard as it cuts. So we go back to Newton's law about to every action there's an equal and opposite reaction, or every force an equal and opposite force. So the forces in turning are largely shear forces, and if you look at the actual cutting edge itself, which is the bit that does the work, it's on centre line, and largely, even though the part's rotating, which you might think we've got an angular force going on, actually we haven't, because the force is only present right at the cutting edge, which means largely as you plunge, as you're into the work and you're plunging in this way, there are several forces at play, and it will largely depend on your tool geometry and on the depth of cut you're taking and the material. There's a whole load of variables in there, but I'm going to generalize just now. So you force the tool into the material that way, which means there is an equal and opposite force in this direction. Back to Newton's law again. So as the work travels, as the workpiece travels past the tool in this direction, there is a cutting force pressing down onto the tool, which causes an almost a downward moment. If you think of where the tool post is, your tool post center is probably back here somewhere, so this is where your center of your tool post goes through here. So that's where the pivot point would be. So as the force is felt by the tool here, if, as I said, if you've got any outer flatness at the bottom of your tool post where it meets your compound slide, you're going to effectively get a bending moment of the tool down because of that force. But again, as I said before, for every force there's an equal and opposite force, so you have also got a force acting in the opposite direction, in that direction, which supports your tool during the cut. If there wasn't that equal and opposite force, your tool would just collapse and disappear. So you've got your two equal and opposite forces that way, and then your third force, which I'm not going to be able to draw because it's 3D, as your tool is traversing into the work this way, there will be an equal and opposite force coming back out this way. So they're general force directions that you've got going on during turning. Now, depending on the geometry of your tool, if you've got a high-speed steel tool with a very positive rake on it, if you think about it, the only bit that's on centre line is the very point itself, and everything behind that is dropping under centre line, which largely, if you were taking a deep cut, would mean your cutting force was actually not vertical, it would be slightly off vertical, so therefore your reaction force in this instance would be slightly off vertical in the opposite direction. And the same is true if you were using a carbide insert with N as the second letter in the 4-letter code, which means you've got a negative cutting angle, exactly the opposite of what we've just described. Then your force is this way, perpendicular to the cutting face, so therefore your opposite force would be going in this direction. So you can see there, just with a couple of examples, how these forces can vary in all different directions. But largely for this example, we're going to talk about the main three, which is the first three I spoke about. So pushing out, pushing up, and pushing back out the board this way, away from the cutting forces. So with that in mind, we're now going to go back to the lathe and have another look and see what that actually means. Okay, so we're back in at the lathe, and all I'm going to do here is demonstrate what push off is on a lathe, and it's basically, in a nutshell, push off, the two things that I've just walked you through there, so the Newton's third law of equal and opposite forces, the number of interfaces we have in this setup here in this system, and also the cutting forces and reaction forces that I've just shown you on the board, all come together into this soup of push off, that we'll call it. The only way to measure all of that push off on the lathe properly, if you want to measure it, is by measuring it from the chuck, which is where your workpiece is. If you try and put the clock anywhere else, you will isolate elements of all of those interfaces in the system. So we've got the DTI magnet on the chuck, and we're just going to wind in. I've got the tool back in the tool post. We're going to wind in to a 0 point on the DTI, which is there. And all I'm going to do now, I'm really fortunate with this lathe. I was kind of hoping in a way that I was going to be able to show you more movement than I'm actually going to show you, but I'm really fortunate that this lathe is incredibly tight. And what I mean by that is, of all those interfaces, I've got very little play, very little slack in the system, which means I cannot show you a huge amount of movement on the clock, which is a good thing. I'm really pleased about that. But if I'd have done this on my old lathe, on my Denford Viceroy, we would have been viewing this in half turns on the dial probably. So this is completely unscientific, because I'm not measuring the force that I'm putting on the system, but I'm now going to gently pull back as close to the tool as I can. I can't pull the tool, I can't grip it hard enough to pull it and influence anything, so I'm going to have to isolate that first interface and pull from the tool post, which is what we're going to do. So if I now pull back on the tool post, you should start to see some movement on the clock, and I think I'm getting about, I don't know, a thou and a half movement on the clock. I don't know if you can see that. It's returning back to 0 each time. So that is a very unscientific way. I'm not measuring anything, I'm just showing you basically slop in the entire system. To measure this I would need some kind of pulling device with a fixed load on it so that I could repeat the load as I was tightening things up and trying to remove some of the play. That is push off. And going back to my tips number 4, where I was talking about balance cuts and the importance of using balance cuts, if I put a much less load on here now, so if I pull at half the strength, I'm probably going to see very little movement, or maybe just a few tenths of a thou movement to simulate a smaller cut that I've got on. And if I was to go for a really tiny cut and I pull very gently, I'm probably going to see no movement at all. So what does that mean? That means if I'm roughing a diameter out and I'm taking 2mm depth of cut, I'm probably going to be influencing quite a lot of that slack in the system, that push off. Then as I get down to my finish cuts and I start taking smaller and smaller and smaller cuts, and I'm measuring between each one and confused as to why I've dialed in 1/2 millimeter and I've actually taken more than 1/2 millimeter off, that's because on my previous cut I took a big cut and now I'm taking 1/2 millimeter cut, which means I'm not pushing the tool away from the workpiece. I'm not taking all of that slack in the system out of the system by putting a big force on it. I'm now taking a tiny cut, which means it's not pushing off, which means the tool is going to effectively cut a deeper cut. And that's why when you don't use balance cuts for finishing diameters, as you start creeping up on your finish size, taking smaller and smaller cuts, your system behaves differently for the different size cuts that you put on it, because you're exerting less force on the entire system, which means your push off changes. So hopefully in that very simple example I've tried to describe what lathe push off is and the importance of using balance cuts right the way to your finished diameter, which what that does is keeps those cutting forces exactly the same all the way in, which means as you come to your finish pass you know what the cutting forces are because you've already dealt with them, you've got them under control, you know what your output's going to be, therefore you're not changing any variables, therefore your finished result is far more predictable. And in a nutshell, that is what lathe push off is, and how balance cuts helps you to overcome that slop that you've got in the entire system. Okay, there's one final thing that often gets confused with lathe push off, and that is part deflection, and they are completely separate. So I've drawn my handy 2-jaw chuck on the board, and we've got a, let's call it a 20mm slug of material in there, and we're turning a 4mm diameter 100mm long, something like that. Now everybody who's done any turning at all knows that's not a good practice and is probably going to end up in either a disaster or a part that's very, very out of tolerance with a big taper on it. So why does it get a big taper on it? Same thing, same Newton's laws at action. So you've got your cutting force in 2 directions. I'm only showing one, which is this way. You've actually got the cutting force going this way and also going this time into the board this way, because we're viewing this from a top view, and you would have the 3 reactive forces in exactly the same way we showed before. So I've showed the reaction force, but what happens here is largely your workpiece is going to be far weaker than the system of interfaces that we've just looked at on the lathe for lathe push off. So largely your lathe won't push off in these cutting conditions because you're not going to be taking big cuts. So typically what's going to happen here is your part will deflect like this against the cutting forces, because the reaction forces won't be able to overcome the cutting forces, which is largely the material yielding against the cutting forces. It cannot sustain the reaction. So that is not push off on a lathe, that is material deflection under load, and that's true of any machine. If you're trying to machine something stuck out of a vise on a milling machine that's a long way unsupported, and you try and cut it, it's going to make a horrible row and the part's just going to move against the cutting forces. Basic common sense, most people get that, but often confused with lathe push-off, and it absolutely isn't lathe push-off. That's part deflection, and that's not what this video is about. So I hope that's been interesting, useful, given some people to think about. And what I'm more concerned with this is, demystifying lathe push-off. It's not complex, it's really basic, and hopefully I've tried to use the most basic language there to explain what lathe push-off is and how it affects what you're doing. And the answer to controlling that is balance cuts. And it's no different if you've got a £1.5 million CNC, brand new CNC machine, or you've got a 50-year-old 300 quid lathe that you've bought from a second-hand tooling supplier. They will all have slack within the system by varying amounts, and they will all suffer from push-off. And that's why in industry, and this is where I've picked this up from, balance cuts is the way to overcome that, regardless of age of machine, size of machine, value of machine, materials that you're cutting, tooling that you're using. All of that gets completely ignored. You don't need to worry about any of that. If you use balance cuts, you control all of the variables in your system and make sure that you are controlling those right the way to your finished cut, and you're in control and you get good results. So again, want to repeat, if you've not seen workshop tips number 4, there's some really good stuff in there. Go back and look at that. Now you've seen what lathe push-off's all about, and hopefully all of that will come together and make sense. Well, there we go, guys. For the 1 or 2 of you that have made it this far, well done. And now for a couple of disclaimers. So when I wrote on the board and did the diagram of the cutting forces, and I showed 3 cutting forces and 3 opposing cutting forces, that was just purely for illustration purposes only. So in real terms, on a centre lathe while you're cutting, there will be lots and lots of forces at play, probably into the hundreds, I would think, as a guess. And to name a few, gravity, you've got friction in many different places, you've got torque through the spindle, you've got variations and fluctuations in power sources. There's so many things that are all variables in there that will all alter the forces and reaction forces that are going on, which takes us right the way back. So when you think we're calling this lathe push-off, it's not actually lathe push-off. That's a nice machinist engineering-y sounding term for what this actually is. What this actually is very simple. It's the laws of physics, and takes us right back to Newton's third law at the start of the episode. And interestingly, through my career, and I've met some very educated people at points in my career who seem to believe that they're so special that they can actually circumnavigate, bend, twist, dodge the laws of physics. And it's, as entertaining as it's equally frustrating at times. You absolutely can't. There's no point trying to ignore the laws of physics, trying to get around them, trying to bend them, trying to twist them, trying to escape them. They are universal and they are constant wherever you are. So, and what we've just been through there is a good example of the laws of physics at play during a machining operation, and it's called lathe push-off. So the only thing you can do is understand them and then use that understanding to your advantage by getting all of that under control, hence balance cuts in workshop tips number 4. So and on that note, I think we'll call that a wrap. I hope you found that useful, hope you found it interesting, hope it's given a bit of explanation and a bit more depth to the balance cuts and the reasons why that is a really good thing to do. And I think we'll close at that. So as it says on the board, it's time for me to push off. So we will catch you all very soon on another video when we'll be making something else.